Imagine it's 3 a.m. You're a cybersecurity analyst.
Right, the worst time for an alarm.
Exactly. An alarm goes off on a critical corporate server. You isolate the suspicious file, detonate it in a safe digital sandbox, and suddenly your screen is just flooded with like 10,000 lines of chaotic alphanumeric gibberish.
And you're just staring at it.
Yeah, you're staring at network telemetry, obscure file system modifications, registry tweaks. You have to figure out exactly what this malicious file is trying to do, and you only have minutes before the real attack might deploy across your network.
No pressure.
None at all.
No.
And obviously, you can't just read 10,000 lines of code, so naturally you turn to artificial intelligence for help.
But, and here's the massive bottleneck for that analyst. You can't just copy and paste those 10,000 lines into ChatGPT or Gemini or Claude.
Right, because of privacy.
Yes, exactly. That detonation report might contain sensitive traces of a highly classified corporate breach or, internal IP addresses, proprietary code.
Which you absolutely do not want floating around.
No. Sending all of that to a third-party server hosted by some massive tech giant is a severe data privacy violation for most enterprises. So, you are stuck.
Well, welcome to the Deep Dive. Today, our mission is exploring state-of-the-art generative AI papers, the real foundational work shaping the future of this tech.
And we have a great one today.
We really do. We are looking at a fascinating new paper from researchers at the University of Kent titled Small, Free, and Effective: Orchestrating Open-Weight Small Language Models to Outperform Single LLM for Malware Analysis.
Quite the mouthful.
Yeah, researchers love their long titles. But whether you are a cybersecurity pro hunting threats or you're just someone fascinated by how AI is evolving, this deep dive is a shortcut to understanding a massive shift in technology.
It really is a paradigm shift.
Because we are going to look at how a team of tiny, free, private AI models can actually outsmart massive, expensive tech giants.
Which completely flips the conventional wisdom on its head. I mean, the assumption in tech right now is that reasoning requires scale.
Right, like trillion parameter models.
Exactly, trillion parameter models running in massive data centers. But this paper is like a David versus Goliath scenario.
Yeah.
Played out on consumer-grade hardware you could literally buy at a local electronics store.
Okay, let's unpack this. We established that sending sensitive malware data to the cloud is just a non-starter. So security operations centers, or SOCs, want to use what we call small language models, SLMs.
Right. And operationally, the researchers in the study define these SLMs as open-weight models under 8 billion parameters.
Okay.
The crucial metric here is that they need to run locally on a single consumer graphics card, specifically an RTX 4090 GPU utilizing something called 4-bit quantization.
Hold on, 4-bit quantization. I see that phrase thrown around a lot in AI spec sheets. Does that just mean we are, like, dumbing the model down so it fits on a smaller chip?
It is more akin to compressing a massive neural brain into a shoebox.
Okay, I like that visual.
Yeah, normally an AI stores the mathematical weights of its neural network with high precision using 16 or maybe 32 bits of memory for every single number.
Which takes up a ton of space.
Right, it requires massive amounts of expensive server RAM. Quantization mathematically compresses that precision down to just 4 bits per number.
Wow.
The model loses a tiny fraction of its nuance, sure, but suddenly an incredibly capable language model fits entirely onto the memory of a standard gaming graphics card.
So the data never leaves your building.
Exactly. It's entirely private, no vendor lock-in, and essentially zero cost to run after you buy the hardware.
That sounds like the holy grail for a security team. But, I mean, I'm assuming there is a catch. If we compress the brain into a shoebox, it's not going to be as smart as a trillion-parameter cloud giant.
Oh, absolutely not. The capability gap is severe. Individually, these tiny SLMs just cannot handle a massive detonation report. The researchers identified 3 characteristic failure modes.
Let's go through them.
First is context overload. A 10,000-line report exceeds the model's memory window, so the AI simply truncates it.
It just chops off the end.
Yeah, it literally chops off the end of the report, which, might contain the exact line of code showing the data theft.
Well, that's not helpful. And the second failure mode?
Domain knowledge gaps. A general-purpose small model might know how to write a Python script or, draft a polite email.
Sure.
But it doesn't intuitively understand the intricacies of the EINER ATT&CK framework.
Real quick, we should define that for you listening. The EINER ATT&CK framework is essentially the global encyclopedia of hacker tactics. It's a matrix that categorizes exactly how adversaries operate, step by step.
Right. And the small models simply haven't seen enough of that specific dense framework in their training data to reason about it effectively.
Makes sense.
And the third failure mode stems from that surface-level pattern matching.
Yeah.
Because they lack deep knowledge, they just scan for buzzwords.
Oh, so they just guess?
Basically. They see the word crypto in a log and immediately jump to the conclusion that it's a ransomware attack, rather than tracing the actual causal chain of how the software executed.
It sounds like dropping a single small language model into a cyber threat scenario is like hiring a highly motivated but super junior employee.
That's a great way to look at it.
They are eager to help. But if you drop a highly technical 10,000-page forensic report on their desk, they are just going to panic. They'll skim the pages, look for words they recognize, and give you a rushed answer so they can escape the pressure.
You could push that analogy even further, actually.
Oh, really?
Yeah. They are junior employees who are terrified of looking incompetent. So instead of admitting they don't know, they just make up highly convincing, confident-sounding lies based on the 3 sentences they did manage to read.
Oh, wow. Yeah, the classic hallucination problem. So what's the management strategy here? How do we organize these junior employees to do senior-level work? Because we know they can't do it alone.
To figure that out, the Kent researchers first evaluated the baseline gap using Meta's cyberseval malware analysis benchmark.
Which is a pretty standard test, right?
Yeah, it's a grueling test of how well models can answer complex, structured questions about detonation reports. They tested 11 open-weight SLMs, 3 specialized cybersecurity models, and 6 massive frontier LLMs, like Claude and Gemini.
Give us the baseline numbers. How bad was the junior employee on their own?
The absolute best single open-weight SLM model called Quen34B only hit a 16.58% overall accuracy.
Ouch. That is not great.
No. Meanwhile, the best single ungrounded frontier LLM, which was Gemini 3 Pro Preview, hit 34.77%.
So the massive cloud models are essentially twice as capable out of the box at understanding these complex cyber threats.
Exactly.
But we have to close that gap without sending the data to the cloud. This leads us to the concept of orchestration. If one junior employee fails, maybe a highly structured team of them working together can succeed.
And what's fascinating here is that the researchers didn't just guess at one team structure. They systematically tested 3 distinct ways to organize the AI agents before they found the breakthrough.
Okay, what was the first one?
First, they built an agentic system. This is a multi-agent pipeline where the AI is given specific digital tools.
Tools like what?
Like command line tools. Instead of forcing the AI to read the entire massive report at once, it uses grep for finding text patterns and JQ for extracting structured JSON data. It actively searches the logs and extracts only the relevant snippets of evidence.
I see. So it's like giving the junior employee a highlighter and a sophisticated search function so they only read what matters.
Precisely. The second approach was a consult system. This functions as a hierarchical loop.
Like a boss and an employee.
Sort of. You have a general-purpose SLM that owns the primary task, but it can ask targeted sub-questions to a second, highly specialized cyber expert model.
Got it. The junior employee can knock on the door of the senior cyber analyst whenever they encounter a piece of code they don't understand.
Exactly.
That makes logical sense in corporate hierarchy. What was the third structure?
A debate system. This relies on an adversarial framework. You take 2 small language models and force them to critique each other's reasoning over several rounds.
Oh, I love that.
Yeah. Agent A proposes an answer to the malware question. Agent B points out the logical flaws in Agent A's answer. Agent A revises its stance, and so on.
I love that concept. Having the models talk it out and argue with each other. I'd imagine forcing them to defend their answers in a debate system really pushes them to think deeply and catches those surface-level mistakes.
You would assume that, but the data revealed a critical, almost fatal flaw when AI models argue without strict external boundaries.
Wait, really?
Yeah, the researchers documented a phenomenon they called a drift.
Here's where it gets really interesting. Because I know they ran these debates over multiple rounds, sometimes up to 10 or 15 rounds. What actually happened to the answers?
Well, when analyzing the pure debate system, they noticed a massive divergence based on the difficulty of the specific questions.
Okay.
On the hardest, most complex behavioral reasoning questions, multiple rounds of debate, hitting a sweet spot around 7 to 10 rounds, actually improved the model's performance.
So the adversarial critique worked there.
It did. It exposed flaws in complex logic.
Yeah.
But then they looked at the easiest questions on the benchmark.
Let me guess they overcomplicated it.
It was worse than that. The debate actively degraded the model's performance on the easiest questions.
Wait, what?
Yeah, the more the agents argued, the worse they performed on straightforward, factual, evidence retrieval queries.
Wait, that makes no sense. If you have two intelligent systems and you give them more time and more processing power to think about a simple question, they should lock onto the obvious answer immediately. How does adding more brain power in debate make them perform worse?
It comes down to the underlying objective the AI is prompted to fulfill.
Which is to argue.
Exactly. These agents are instructed to critique, debate, and find flaws. If a question is incredibly simple, like, what IP address did the malware contact, and the first agent gets it right immediately, the second agent is still mathematically compelled to argue.
Because it's told to find a flaw.
Right. It looks at the correct answer, looks at its instructions to find a flaw, and just starts grasping at straws.
So they're hallucinating just for the sake of being contrarian. Because their core directive is, you must argue. They literally cannot just say, yep, I agree, good job.
They cannot. To fulfill the prompt, they start pulling in tangential, completely irrelevant information from those 10,000 lines of logs just to justify their required critique.
Oh my goodness.
Yeah, they might grab a completely benign IP address from a normal Windows update process and argue that it is the malicious one. This tangential drift pulls them away from the obvious correct answers and drags them into the weeds of incorrect alternatives.
That is wild. They literally argue themselves out of the truth.
If we connect this to the bigger picture, it proves a vital point about generative AI. Peer critique is useless or even actively harmful if it isn't grounded in verifiable facts.
Right.
Just having two intelligent agents talk to each other doesn't guarantee a pathway to truth. Unconstrained, it just generates increasingly sophisticated fiction.
Okay, so peer debate causes drift on easy questions because they just invent things to argue about. But we still need that deep reasoning for the complex questions. We do. And looking back at the first system, the agentic one using grep and search tools, that one is great at finding hard evidence, but lacks the deep reasoning. So the obvious solution is we have to mash them together.
The researchers reached the exact same conclusion. This brings us to the ultimate breakthrough of the paper, the hybrid system.
Let's get into it.
They realized they had to constrain the AI's tendency to drift by forcing the debate to use the digital tools from the agentic pipeline.
How does that actually look structurally? Walk us through the workflow for the analyst.
It operates in three rigid phases. Phase one is evidence collection. The pipeline ingests the raw detonation report,
Okay.
but it also enriches it by actively pulling in tactical descriptions from that external MWATT and CK database we mentioned earlier.
Adding the expert context.
Yes. Then, the tool search agent uses those command line tools grep and JQ to pull out highly relevant snippets from the raw code. Finally, an evidence miner scores these snippets using cosine similarity.
Okay, stop right there. Cosine similarity sounds like trigonometry from high school. How did that mathematical concept apply to text logs?
Think of it as a mathematical compass. The system converts the user's question and the extracted code snippets into numerical vectors, essentially arrows pointing in a mathematical space.
Okay, I'm with you.
If the arrow for the log snippet points in the exact same direction as the arrow for your question, they are highly related. If they point away from each other, the snippet is discarded.
Ah, that's clever.
It ensures we only keep the most relevant facts. So phase one creates a rock-solid, mathematically verified evidence bundle.
We have our stack of highlighted verified facts. Then what?
Phase two is the debate, but with a strict grounding constraint. They paired Qwen34B, a strong general model, with Foundation Sec 8B, a cyber-specialized model.
The junior employee and the senior analyst.
Exactly. They debate for 7 rounds, but the researchers enforced a hard rule. The agents must explicitly cite the collected evidence from phase one.
They can't just make stuff up.
Right. If an agent makes a claim, it has to point back to the evidence bundle. Finally, phase 3 introduces a verifier agent. This acts as a quality gate, checking the final answer to ensure it actually matches the cited evidence and isn't a hallucination.
So previously, in the pure debate, there were just two people arguing in a bar at 2 a.m.
Exactly.
They could bring up whatever crazy theories they wanted just to keep the argument going. Now it's a strict courtroom.
That's a perfect analogy.
The lawyers, the two debating AI models, can argue all they want, but the judge, the verifier, forces them to point directly to Exhibit A in the evidence box. If they try to introduce a theory and can't cite the exact hex code extracted in phase one, their argument is just struck from the record.
That courtroom dynamic is exactly how the architecture functions in practice. By forcing the debate to stay tethered to retrieved evidence, they completely eliminated the drift problem on the straightforward questions, while preserving the brilliance of peer critique on the complex behavioral questions.
Give us the numbers on this hybrid courtroom system.
The results represent a massive leap. This SLM hybrid system achieved 35.30% overall accuracy on the CyberSeval benchmark.
Let me check my notes here. The best single open-weight SLM, acting alone, was 16.58%.
Yep.
They more than doubled the intelligence of the exact same tiny model just by organizing its workflow and forcing it to use tools.
It outperformed every single SLM configuration they tested, but the most important comparison is this. 35.3% means it beat the best ungrounded frontier LLM.
The giant.
Yes. Gemini 3 Pro Preview scored 34.77%. The tiny, free, local models, orchestrated effectively, actually outperformed the massive cloud giant.
David beat Goliath. And we have to talk about the financial reality of that victory for the listener, because running tens of thousands of malware reports through Gemini or Claude is going to drain an IT budget immediately.
Oh, the financial disparity is vast. To run the full benchmark suite just one time using a model like Claude Opus 4.5 costs over $96 in API fees.
Just for one run.
Right. To run it on the local SLM hybrid system costs exactly $0 in API fees. It's completely private, happens entirely on your local server rack, and gives you better accuracy.
That is just incredible. But benchmark numbers are great for a research paper. I want to know how this actually looks in the real world.
Yeah.
Because malware authors aren't writing code to pass a static multiple choice test. They are writing incredibly sneaky, deeply obfuscated code to steal your banking data or hold a hospital's network hostage.
The Kent researchers understood that static benchmarks have limits, so they took their hybrid system into the wild.
Nice.
They tested it against novel, highly sophisticated malware samples from early 2026 that exhibited evasion techniques the AI had never seen during its training.
The ultimate test.
And the qualitative difference in how a single massive LLM handles these real-world threats versus the hybrid system is really eye-opening.
Let's look at the first case study from the paper, UNC 5142. This is a threat campaign using a technique called ether hiding.
A very clever technique.
Yeah, for you listening, basically, instead of hackers hiding their malicious download links on a regular web server, which security tools can easily flag and block, the hackers hid the malicious payload inside the data fields of smart contracts on the Binance Smart Chain.
Right.
The blockchain itself was hosting the malware. It is a wildly clever evasion tactic. So how did the single massive LLM handle this detonation report?
The single Gemini model failed completely, and the reason it failed reveals a major vulnerability in large models.
Such as?
LLMs prioritize human-readable natural language over obscure code syntax. When the single model read the report, its attention mechanisms heavily weighed the blockchain terminology words like contract, Binance, and transaction.
Oh, so it got distracted.
Yeah, it lazily guessed that the file was just crypto mining software trying to steal the computer's CPU power to mine coins. It explicitly told the analyst it couldn't find a direct malware download URL. It totally missed the actual threat.
And how did our hybrid courtroom handle it? How did it bypass that surface-level illusion?
In Phase 1, the agentic tools physically forced the AI's perspective. By using grep to search the raw transaction logs for anomalous string lengths, it successfully isolated the exact chunk of hexadecimal payload data hidden in the blockchain traffic.
It ignored the human words and found the hidden math.
Exactly. Then, in the Phase 2 debate, the general agent initially got confused and still thought it was a payment processing script.
Typical junior employee.
Right. But the cyber expert agent stepped in, cited the specific anomalous hex data extracted in Phase 1, and proved that the contract wasn't processing cryptocurrency tokens. It was serving immutable data blobs consistent with the ether hiding technique.
Ooh.
The hybrid correctly classified it as a downloader and extracted the exact Binance Smart Chain address serving the payload.
Wow. By forcing it to look at the math rather than the words, it completely saw through the disguise.
It did.
Okay, let's look at case B, which is arguably much sneakier because it targets the human. Luma Stealer, using a tactic called click fix.
This one is brutal.
It really is. If you are listening to this, you might have actually seen this one pop up in your computer. It throws a fake Google Chrome update overlay on your screen.
Yeah.
It tells you there's a display error, and to fix it, it tricks you into copying a PowerShell command into your clipboard and pasting it into your Windows Run dialog. It bypasses the browser's security by tricking you into executing the code yourself.
It is a brutal social engineering tactic. And once again, the single large LLM fell for the trick.
It read the human words again, didn't it?
Yes, it read the visual lore text in the detonation report, the actual words update Chrome and display error, and classified it as a simple credential phishing site meant to steal passwords. It completely missed the fact that a system-level PowerShell command was being executed.
But the tiny hybrid system caught it. How?
Phase 1 used its microscopic tool search to find hidden HTML clipboard event handlers. Specifically, it grabbed on-copy and on-click JavaScript events that were buried in the page source.
So it dug deep.
It pulled those obscure tags out into the evidence bundle. In the debate phase, the expert agent looked at those handlers, saw the hidden PowerShell command that was being loaded into the victim's clipboard buffer, and successfully linked that exact execution chain to documented Luma stealer behavior.
So what does this all mean? It tells you that if you just rely on a massive model to read a report top to bottom, it's going to fall for the surface-level illusion, just like a human would.
Exactly.
The single model sees the words Chrome update, and its reasoning just stops. You need that microscopic tool search to pull out the hidden JavaScript, combined with the structured debate to interpret what that script is actually trying to achieve.
So first-level reading completely fails against modern obfuscated malware. The underlying architecture is what creates the intelligence, not just the size of the neural network. And we have to include a vital point of nuance here. The researchers ran a fairness check. We established that the SLM hybrid beat the ungrounded Gemini model. But what happens if you take that massive Gemini model and plug it into the exact same agentic evidence pipeline?
Oh, that is a great test. What if Goliath gets to use David's tools? Does the giant get even smarter if you force it to use the courtroom evidence box?
It does. When they ran Gemini through the hybrid architecture with the tool-assisted evidence collection phase, Gemini's accuracy jumped to 38.22%. So if you match the evidence grounding, the frontier model's larger reasoning capacity still wins out.
That makes perfect sense. The massive model inherently has a wider knowledge base, so if you spoon-feed it the same mathematically verified evidence, it's going to draw slightly better conclusions.
That's the scientific reality. But that doesn't change the operational reality.
Right, because of the cost and privacy.
Exactly. For an enterprise SOC that requires local processing, $0 API costs, and absolute data privacy, achieving 35.30% with a completely free local SLM hybrid is a massive immediate triumph. It proves that orchestration is just as critical as raw parameter count.
It is a total paradigm shift for how security teams can build their infrastructure. But before we get too carried away and let the AI run the entire cybersecurity department while we sleep, we need a reality check.
A major reality check, yes. While 35.30% is a massive breakthrough for open-weight models on this extremely difficult benchmark, it is absolutely not high enough for autonomous decision-making.
Right.
The researchers are explicit. This is an analyst assistance tool.
Yeah, if the AI is still getting a significant portion of these complex behavioral questions wrong, or even just partially right, you can't just let it automatically delete files or sever network connections.
If you trust the AI blindly, your SOC will suffer from severe alert fatigue when it hallucinates, and you might miss critical network-destroying threats.
So the human has to stay involved.
A human expert must remain in the decision loop. The true value here is that the hybrid system provides a fully documented evidence bundle alongside its answer.
Oh, I see.
The human analyst doesn't have to search the 10,000 lines. They just look at Exhibit A, verify the AI's logic, and make the call. It accelerates the human. It doesn't replace them.
So, to summarize today's mission for you listening, orchestration, and specifically combining microscopic evidence retrieval with structured, grounded debate, can make small, cheap, private AI models highly capable at incredibly complex reasoning tasks.
Absolutely.
You don't always need to pay for the billion-dollar cloud model if you know how to manage the free local models correctly. You just have to give your junior employees the right digital highlighters and force them to prove their arguments in court.
This raises an important question, though, and it's something I want to leave everyone thinking about.
Worth hearing.
We've seen today that forcing AI models to debate purely based on retrieved, verified evidence completely cures their tendency to drift or hallucinate when they get confused by technical reports.
It eliminates that urge to just invent tangential arguments to sound smart.
Right. It makes you wonder if this rigid, evidence-grounded debate framework can turn a disorganized team of junior AI models into a master cyber analyst, What would happen if we applied this exact same orchestrated debate structure to our own human teams when making high-stakes business or personal decisions?
That is a great point. Next time you're in a boardroom and someone starts drifting into a hallucinated tangent argument, just ask them to point to Exhibit A.
Mm.
Until next time, thanks for taking the deep dive with us.